Our first topic for this week is kind of a basic topic, so we're going to fly through this really quickly because most of us are familiar with the different types of graphs that are used to display data. So we're going to take a little bit of time to go over some of the finer points of them and point out some of the details, but we're not going to spend a lot of time on any one of them. So let's start out with graphs for categorical data. Remember, categorical data are data that the answer to the question being asked puts you into category, like favorite color or any question that's yes or no. One of them is a bar graph. I'm assuming most of you know what a bar graph is, so we're going to jump up to double bar graphs or double bar charts, where we're using categorical data, but we're comparing two different variables to each other, or two different treatments of the same variable to each other. So how do we do it? It's constructed just like any other bar chart, but we're going to have two sets of bars, two groups of data instead of just one. We can use relative frequency. If the two items don't have similar ranges, we use relative frequencies so that we can compare them. Now here it says we must, but that's not necessarily true. If we're comparing something that's the same variable with just two different treatments, like federal budget for 1 year compared to the next, or the national debt compared to the federal budget, we can use the same axis and use just raw frequencies. We don't have to convert them to relative frequencies. But if we're using things that are very, very different, we use relative frequencies so that they can fit on that same vertical axis. And then we must include some sort of a key to denote which bar represents which data set. So if we're going to color code the bars and let green be 2017 and blue be 2018, we have to specify that somewhere. Or the alternative to including a key is we can just make sure every bar is labeled very carefully. So for example, each year the Princeton Review conducts a survey of students applying to college and of parents of college applicants. 2009, 12,719 high school students responded to the question, ideally, how far from home would you like the college you attend to be? Also, 3,007 parents of students applying to college responded to the question, how far from home would you like the college of your child attends to be? Data is displayed in the frequency table below. Now here, because the total frequency or total amount for the students is way larger than the total amount for parents, this is where we have to convert to the relative frequency. If we had picked a number like 12,000 and surveyed 12,000 new college students and 12,000 parents, so that total number was the same, the sample size was the same for both, then we could have compared raw frequency instead of having to convert relative frequency. So our table down here shows that data. What should we do first? Well, we convert them to those relative frequencies. So we divided each frequency by the total frequency for that data set. So the students was by that 12,700 and whatever, and the parents by the 3,000. And we get the relative frequency for each. So now we put each category, the less than 250 miles, the 250 to 500, 500 to 1,000, each of those categories on here, and then we have the parents and the students. Notice we have the key here showing that the students are blue, the parents are orange, and we can see the relative frequencies, where majority of parents want their students to be closer to home, and slightly more students want to be closer to home than further away, and on down the line. We can have a segmented or a stacked bar. So again, we're using it for categorical data. Again, we should use relative frequencies unless, just like before, if the sample sizes from the two data sets, or sometimes more than two, if the sample sizes from all the data sets are the same size, we don't have to convert to relative frequency, but in most cases we will, just to equalize out that size. We draw the bar representing 100% for each group, and we divide the bar into segments corresponding to the relative frequencies within each category. So for our parents here, now rather than saying, putting the miles across the bottom axis, it's going to be the parents and students across that bottom axis. So we still create the relative frequencies, only now each bar represents the whole amount, or that 100%, or the 1. For students, we take their 100% and we divide it up. We put on bottom here in the blue is the less than 500 or 250 miles, and the 250 to 500, and up through the list. Then we do the same for parents. And we have to have a key now specifies which of these categories each of the colors represents. So what this is showing is the total, all of the students and how it's broken down within the students, and all of the parents and how it's broken down within the parents. So it displays the same relationship, just a little bit different manner. We're relating each of them back to their own population instead of comparing each category between students and parents. A pie chart is actually very similar to that segmented bar chart. Again, using categorical data, and we are representing the whole data set again. Each slice is a relative frequency times 360 degrees. Now, we're not going to use a protractor. We have technology to make those perfect, so we're not going to worry so much about measuring out the degrees. This is used to describe parts of the whole. So we're looking at a resume here, looking at the number of typos found in different resumes and the frequency. So the number of resumes in this set, 60 resumes had 1 typo, 10 resumes had 4 or more typos. Not really sure what they mean by don't know here. Maybe they just weren't sure if it was a typo or if that's what they were really trying to say. So up here, we convert each of those frequencies into relative frequencies. We draw a full circle. That circle represents 100%. So a relative frequency of 0.4 is 0.4 times 360 degrees. Because 360 degrees is the full circle. That's 144 degrees for that slice. So here's that 40. And notice this percent here, 40% represents the 0.4, 36% the 0.36. Each of those slices is a proportion of the circle. Again, Minitab does this rather well. Excel does this rather well also. So what this chart tells us is a portion of the whole, similar to that segmented bar chart. Now let's look at describing numerical data graphically. So we've looked at those dot plots showing the normal distribution and how we can get the center. So we're going to kind of fast forward through this because we have done mean, median, and mode. And then we have the spread for each of those dot plots. Centers are the same here for each of these, but the spreads are different. So we have the range and we have variance and standard deviation. And we have interquartile range. And of course here we have skewness. So we're going to collect data here by rolling a die and creating a dot plot. We should get a symmetrical distribution there. So we have a bell-shaped curve. Remember, that's what we use to describe that normal distribution. If we collect data by rolling a single die, what shape should we get? It should be uniform because the value 1 through 6 are each equally likely. So it should just be a flat line, no bell shape. We get the bell shape from rolling 2 die and graphing the total, but not from a single die. So to help remember the name of the shape, picture soldiers standing in formation. They're all uniform. So find the age of 5 coins in circulation, current year, minus the year of the coin, and record. What is this shape? It's going to be skewed. They're more likely to be newer. The older they are, the less likely they are to still be in circulation. You have that long tail on that side. This would be negatively skewed to the left, or sorry, positively skewed to the right because the older coins, which would have the higher numbers, are going to be less likely to occur. Suppose We collect data on the time it takes to drive from San Luis Obispo, California to Monterey, California. Some people may take the inland route, approximately 2.5 hours. Others take the coastal route. Because there's two different routes, this would be bimodal, giving us that kind of double hump shape. Because there'll be a peak at each mean for each of the two different routes. Again, I'm flying through this kind of quickly because we've gone through this part before. It's the part at the end here that's really important to this unit, making sure we understand how this data is displayed so that we can move on to the next step, which is analyzing it. Unusual occurrences, of course, outliers are way out. There's big gaps, or there's huge clusters out away from the main body of the data. So looking at those graphs for numerical data, stem and leaf plots we've looked at, very important. Using the leading digits. Also used comparative stem and leaf plots, or sometimes called back-to-back stem and leaf plots, where we have the same stem and two different sets of leaves. So for a single one, here's a set of data. The stem is actually the 10th now. It's very important that somewhere in your chart you specify what the stem is, whether it's a 10th or the tens or the hundreds and whatever. For the observation of 0.32, the stem would be 3 and the leaf would be a 2 behind the 3. Now we put all the numbers in, and then we do have to go back through and reshuffle them to put them in order from smallest to largest. If it were on the left side for a back-to-back or comparative plot, we'd want to make sure we go largest to smallest on the left side. So here's an example of a plot for the median age of in the 50 states and including Washington, D.C. So there's 51 data points there. We cannot really see a distinctive shape just because 2, 3, and 4 is not enough stems, so we can break them down into more stems if we want. 2 high, so that means it's from 25 to 29. 3 low means from 30 to 34. 3 high means from 35 to 39, and so on. Now you get a little bit better shape here. This is kind of bell shape, a little bit skewed on the lower end here because if we tipped it on its side, that tail would stick out a little bit further. For back-to-back plot, we have one stem or a comparative plot, and we have the leaves on both sides. So here we can see that in Central Africa, the values tend to be smaller than in Northern Africa. Histograms then require us to group the data. Unless it's a small number of responses, we can graph each response, a small number of possible responses where we get a higher frequency for each. Then we can graph each response together. So for this set of data, we first have to create some sort of frequency table for it. And then we can graph the frequencies. Now here again, we only had responses from 1 to 12. So there's a limited number of possible responses, so we can graph each individual response separately. If we had a larger number of responses, we'd want to group them together. Now we could use them for continuous data, then we definitely have to group responses together using categories like this. So this is from 0, a little bit sloppy notation, 0 to 2, technically it's 0 to 1.99, and then 2 to 3.99, and so on. So we group them together because we can't show each individual response because there's an infinite number of individual responses with continuous data. Cumulative relative frequency plots we've been over as well. So we just convert our frequency in relative frequency into a cumulative relative frequency. Note that cumulative relative frequency should always be 1 at the bottom of that column. This case came out to be 0.999. That's just round off errors in our relative frequencies. And so then we're going to plot, this is basically a line graph that gets us from 0 up to 1. So approximately 30% of the years here had annual rainfall less than what amount? So we'd find 30%, trace it over. That'd be less than 7 or 8 inches. Well, 7.5 inches. There we go. Which interval of rain amounts had a larger proportion for the years 9 to 10 or 10 to 11? Well, here's 9 to 10, here's 10 to 11. 10 to 11 has a steeper slope. That's a higher proportion. Now, this is the new part for today, bivariant data using a scatter plot. So here we are looking at two different variables, comparing them to each other. So we're using numerical data, and we're comparing two variables. Both variables are numerical. We draw the horizontal scale and make sure we cover the whole range of that independent variable. We draw the vertical scale and make sure that covers all of the values or the whole range of the dependent variable. Then we plot points using that rectangular or XY coordinate system. And then we're going to be looking for, in our next section here, the relationship between those variables. This is called a scatter plot, and this is what we're going to discuss in the Chapter 5 material that is really the heart of this week, in summarizing that data, looking for regression equations and other strengths of relationship. Time series plot, data over time. So a single variable rather than different variations of the variable or different categories of the variable. That single variable just measured at different points in time, as you can see here. So that was just a review of our data graphs. Again, the stress is on the scatter plot for this week, so that we have those fresh in our mind as we start our regression analysis.